I want to mention one more energy concept. It's a very, very short concept, very quick concept. And to get at it, I want to ask what determines who wins a race? When I say race, I mean a race between tortoise and a hare, a running race between two people, automobile, bicycle, whatever, some kind of race. What determines who wins a race from an energy point of view? Clearly, the person who wins the race is the person who's got an average an average speed that is higher than the other. The fastest average speed is going to win a race. But how is it that you can use energy to determine who's going to win a race? And the answer is it is not who has the most energy, but it's who can use the most energy efficiently, or it's really who can use their energy more quickly, right? So it's about a rate of use of energy. Two people who finish a running race can both have energy left over, and hopefully do have energy left over so that they are alive when they cross the line. So it's really a question of who can use energy most efficiently or most quickly. So we discuss the concept of power. Power is the work per unit time or energy per unit time, depending on whether we're talking about the amount of work somebody does or the amount of energy somebody uses, the amount of work some machine does or the energy some machine uses. The power is how quickly it can use that energy, or it can produce that energy, or maybe the how quickly can a machine convert work into energy. But it's a measure of energy over time. Okay, so let's do a quick problem. I just looked up on the internet at a car, 1992 Audi 100, accelerates from 0 to 60 miles per hour in 8.3 seconds. The weight of the car is 3,385 pounds. How much power does the car have? Well, the first thing we're going to do is let's just convert everything to MKS units so we don't get confused. So that gives us 0 to 26.8 meters per second in 8.3 seconds. Then the mass is 1,535 kilograms. So you can do the conversion from miles per hour to meters per second, and you can figure out how much mass weighs 3,385 pounds, and there you go. And so then we want to figure out the power. So the power is the amount of energy or work done divided by the amount of time. So power equals work over time. The work in this case, it's change in kinetic energy, right? Change in kinetic energy over time, which is 1/2 m v final squared minus 1/2 m v initial squared divided by the time, which in MKS units is what we have written here. Therefore, I'll go to a new page to write down the final number. The power of this Audi is 66,415. What are the units? Well, it's energy. In MKS is joules over time, joules per second. And the unit of a joule per second is equal to a watt. That's the MKS unit of energy, or a W. So it's 66,415 watts. So another common power unit is the horsepower, or HP, right? 1 horsepower is 745 watts. So that means this Audi has a power of 89 horsepower. I looked up powers of Audis, and a regular Audi would have a power somewhere in the 80s to 90s of horsepower, and a turbo sort of special large engine edition would have powers of about twice that, 160 horsepower. Presumably the horsepower is approximately the amount of power that a horse has, right? So a car may be like being pulled by 89 horses, and you can actually measure the horsepower by measuring measuring a horse's power by measuring how much weight can a horse pull, and if you have it pulling it upwards, right, then you know the change in energy, the minimum change of energy is the gravitational potential energy. So if you can figure out how much how long it takes a horse to pull a certain amount of weight up a certain distance, you can figure out the power of a horse. And presumably somebody did some measurements at some point and said sort of the average horse pulls 745, has a power of 745 joules per second, can lift can do, well, anyway, we'll do an example in a second to show what that means. 745 watts. Where have we seen the unit watt before? You see it in light bulbs, right? 100-watt light bulb, a 50-watt light bulb, a 10-watt light bulb. So that tells you about how much electrical power, how much energy per unit time that light bulb is using. If it uses 100 watts, it's using 100 joules per second. If it's using 10 watts, it's using 10 joules per second, right? That, I think you get the sense that a few joules is not a lot of energy, so a 10-watt LED bulb doesn't use a lot of energy per unit time. Obviously, if you leave it on for a few years, it uses more and more energy, but it uses the same amount of wattage, right? 10 watts means it uses 10 joules every second. So after a year's worth of seconds, there's 10 to the 7th seconds in a year, so it's going to use, if it uses 10 joules per second, then a year it uses 10 to the 8th joules of energy. That's 10 to the 8th is 100 million joules of energy in a year. Sounds like a lot of energy, but it is what it is. A 100-watt light bulb uses 10 times that, right? It uses 1 billion joules of energy in a year. So, saying that another way, a 100-watt light bulb uses 100 joules of energy every second. So, in, for example, 1 hour, it uses, right, since power is energy over time, energy is power times time, it uses 100 joules per second times 3,600 seconds, or 360,000 joules per hour. A 10-watt light bulb uses 36,000 joules per hour. So power is a useful concept to relate energy used over time. So, like talking about the horse lifting a mass, let's just talk about an elevator lifting a mass. I'm just estimating the elevator in Martin. Let's say it can lift 1,000 kilograms, going from the first floor to the 5th floor, so it's going up 4 floors in 10 seconds. Let's assume that a floor is about 3 meters, so it's going up 12 meters in 10 seconds. And let's figure out how much power the motor in that elevator must have. So the amount of energy is at a minimum mgh, right? If it gives it a velocity, significant velocity, it's got to use more energy. But the minimum is the change in potential energy due to gravity. So it's 1,000 kilograms times 9.8 meters per second squared times 12 meters, because it goes up 12 meters, which is 117,600 joules. So the power is the energy over time, and I'm just assuming about 10 seconds to go up 4 floors. Maybe it's a little more. But that ends up giving us 11,760 watts. 11,760 watts. Watt is the MKS unit, but if you like the horsepower, then that's 15.8 horsepowers. 15.8 horsepower.